Recording. Here I give you some practical hints about selecting the operators. And mentioned here is in facts, but it doesn't really limit to facts. I think you find other software also allow you to select the operators. And then some algorithms, or the software package, they have their internal operators, but they do not allow you to change the operators. And some very intelligent version, they even try to tune the algorithm for you, okay? But anyway, here, you see that I've written here for discrete variables. So 1-point crossover, uniform crossover, they are something recommended. And in my experience, I use quite heavily uniform crossover and also uniform mutation. The reason also because of, I mentioned before that for manufacturing and supply chain problem, quite many of them are discrete variables. So that's why discrete, if you, and then later you can see that if you have a mixed integer problem, then it's also recommended that you use the discrete variable operators. That means either 1-point or uniform. So practically, I choose very often using uniform crossover. But if you have a problem that are continuous variable in nature, then here you have the blend crossover and even more advanced form called the simulated binary crossover by Professor Depp. These are the options you can find in Factor Analyzer or other software. How do they work? And before we look at them, we can also check about the weight, about the probability weight. According to de Jong, already in 1975, so early, he was one of the students of John Holland, if I remember correctly. So these are the golden rule. Until today, I think people do not really get away from that, except if they want to make a very high customization. Population size of 50, crossover weight of 60%, 0.6, and then very low mutation weight, 0.05. So for 100 of the bit, if you have 100, you will expect that with this mutation weight, you will just have 5%. That means only 5 of them of the bit will be mutated if you look at the binary string. So this was some recommendation already from the very beginning of the genetic algorithm history. But when we look at the operators, we already talked about the 1-point random crossover point. And then for uniform, you could see that you try to, from both of the parent, but then bit by bit, you try to use the uniform probability in order to get the features from both the parents. And then you could see that the variety of the solution is much higher than the 1-point crossover. And in integer optimization, we find that uniform crossover usually is useful. The reason was because of it also introducing more diversity. So we find that uniform crossover, they usually give to be more useful, especially in the case of multi-objective. And then more advanced form, especially called continuous variable, we look at the blend crossover. They have an alpha as a parameter to control. And you have 2 parents, xi1 and xi2. The T simply means that it belongs to the current generation. So you are working to generate the offspring for the generation T plus 1, but now you have 2 parents from the generation T, 1 and 2. The idea is that you want to combine the features from these 2 real variables, but at the same time, you don't want to deray that much. So that's why you use an alpha to control it. Okay. And then the alpha will control about, let's say that if the alpha value, so read here, so the LBX alpha, they have an interesting property. The location of the offspring depends on the difference in the parent solutions. So because of is x2 minus x1, one of the parent value minus another parent value. And if the difference between the parent solution is small, then the difference between the offspring and the parent solution is also small. And this is what gives you a general genetic algorithm behavior is that the longer you run, when then the solution become converged and they are more identical in terms of giving you the fitness value, then you could expect the parent one and the parent two will have the value more closer. And then, of course, based on the alpha you select, but no matter what alpha you select, you could imagine that when the x2 minus x1 value becomes smaller, then of course the difference of the new offspring to the original parents will also be smaller. And more advanced form by Professor Deb is this called the simulated binary crossover. Okay, unlike the bland crossover alpha, you select from a range, okay? You limit it from a range. It actually associates a certain probability distribution functions across the parents, okay? So the chance that you will select a solution will be covered by the graded area or the area covered by the probability curve here. So he used polynomials to define these two, this shape here. And then you have another called the lambda parameters. And this lambda parameters is called a distribution index. So what does this distribution index do? Look at the value here. If you have a solid line, it means there is a value 2. And then if you get a higher value, like the 5, it will be the dashed line. Okay, when you look at this figure, you should ask yourself, so what the value of this distribution index will give you so that you have the higher chance that you will fall into a range or value that is closer to one of the parents. So I give you like 5 seconds to look at that and then think about that. So the higher value of your distribution index will actually make it more narrow when it comes to like the range that you could select closer to the parent or one of the parent, because the distribution shape cover both the parent, but then you use the index to control how close they could be. And of course, if you have a lower value in the beginning, you could make this an adaptive parameter so that you could change the distribution index, change during the course of the optimization. This will be an advanced form we call adaptive. But the idea is still the same. That means if you choose a lower value, it means that you can have a value that will be higher difference with a higher deviation from the parents. That means you are doing more explorations. You try to explore what could be like other possible good solutions. But in the later phase of the optimization, when you want to exploit and when you want to explore more deeper into the search space, a particular reagent, then you should narrow down so that it become closer. So again, this is exactly about what we described about the well balance between exploration and exploitations. And practically, you could move this into, I think here just like repeating, similar to the BLX, is about the distance of the offspring to the parent are also controlled by the difference between the parents. So if their original solution, they are far away, then of course, choosing the solution will not be closest to both parents. But when the parents are very closer, then you have the distribution more accumulated around the parents here. Then of course, the chance that you select the value coming from this range that cover here will be much higher. So this is how you can control by both what you can control is the parameters about the distribution index. What you cannot control, but then later you will converge when you have the solutions getting together more in the convergency. And then this slide tells you about the bounded and unbounded case. The probability distribution is a function polynomials that cover a larger range As you could see that now here's a much longer tail. But then if you are aiming at a constrained problem, that means you have a lower bound and upper bound here. So of course, you are not allowed to choose a value outside your constraint and make them infeasible. And then by having the constraint there, then the area need to be adjusted. And that's why with a bounded variable, the shape will be adjusted, and then also the chances that you get back to the range will also make sure to be 100%. The reason was we are going to select only the area bounded by the dashed line, as you could see there. And that's why unbounded was the original SPX, but then with the constraint that you become the bounded reagent. And then the algorithm, if you work with a constraint problem, then of course the algorithm need to be adjusted in terms of calculating the distributions. And finally, when it comes to the mutation, the concept looks very similarly. I don't think I will go deep into the details or more because the mechanism works similar. But now instead of you combining the genes, now you're talking about you process on the individual genes. And then we talk about 5 to 7% of the mutation on the variables on the average. That is based on the rule of thumb. And then this will be the example here. Again, this will be applied to, let's say that if we have a uniform range or uniform delta, we use a uniform distribution to find that across a 30 input variables, and they are discrete variable, for example. So if you follow this mutation rate of 0.05, then you will know that there will be only 2 variables will be mutated on average. If your mutation weight become too high, then you will closer and closer to be a random search because you rely more on the randomization to interpret the good genes that you already find. So you are doing more exploration than the exploitations. But then if you make it too low mutations, then that means pretty much you just rely on the crossover to combine the best feature, but you do not really explore if there are some other good features that you can find outside the range of the covering by the current parents. And that's why to adjust the parameters, it is actually a very interesting research topic. But this topic is usually associated with a particular application. I had a PhD student who graduated 2018. He was one of the key developers for fact analyzer, but in his PhD thesis, his subject was just to study how we can tune the optimization algorithm to do better. And then he even developed an bi-level optimization. And this topic is about you use an optimization to tune the optimization parameters of another algorithm. So that would be something really interesting and then a bit more complicated to be covered in this lecture. So for mutation, the uniform delta and uniform range, for uniform delta, the concept looks pretty similar, except that we don't have a alpha here. You could also use the alpha to control things here. But now instead of processing on a parent, you see you don't have two solutions. You are talking about your current value of your variable, and then how will be the interpretation, of course, within the range of lower bound and upper bound. The delta will control how much the value change from the current value to the real new value. And then for uniform delta, you will have a random mutation between the range. So delta become a random function instead of a delta, instead of a value. But again, you use a randomization to select a value bounded by your range there. You can have a more advanced like normal distribution or the polynomial, like in the case of XPX. But in this case, again, we are not processing combining two parents. We are only talking about how we can interpret a single value for a single variable. So any questions to me now, you can write down on the chat, but or later we can discuss. We move on to talk about multi-objective. We already a little bit slowed down, but then When we look at a simple production engineering problem, you could find it also in supply chain about the warehouse. This slide simply tell you a very simple model that you are going to work in your lab. So it's that simple. You have 6 stations and then you have a buffer in between. So when you try to optimize, and then the problem is called the optimal buffer allocation. So where do you allocate the buffer? And this problem, even though is deceitfully simple, but practically is actually very important, especially when we work with a discrete manufacturing. So if you work with process industry, then you don't need to bother about the buffer, the warehouse, inventory in between. But for discrete manufacturing, I think all discrete manufacturing process, they need to have a certain warehouse and buffer. You may go for this lean manufacturing, but if Matthias, when he cover in his lecture about the variability, you talk about factory physics. We know that in real life, because of variability, so in most of the cases, you can't simply avoid that you need to have some buffer. In the factory physics term, they have a capacity buffer. They also have this time buffer. But in here, when we talk about optimal buffer, we talk about the inventory buffer. That means how you can store the inventory in between. So when you work with the lab for chapter 8, you will find yourself how big will be the difference when the buffer change will affect the performance. But when we talk about performance, are we talking about maximizing the throughput, or are we talking about minimizing the work in process cycle time? And according to factory physics, which later we will also look at the one slide so that you can refresh your memory, you should remember that the throughput and work in process, they are actually in conflict with each other. So whenever you have objective, they are conflict with each other. Normally, you have a two very simple way to do if you don't have any advanced algorithm to help you. One is we already did it before. You combine the profit, we combine the money you spend on buying the machine, and then you spend on the buffer, and then you minus those value in the same objective, but then you plus the value about the money that you earn by selling the product. So this is very common that you combine the performance measures into a single measures, and commonly it can be the cost or profit because of the ultimate goal of many companies is to earn money to have the profit, or at least they should minimize their cost. And then there is another interesting method that you can also do it by yourself already is you always treat one of the performance measure as the key performance, and then you keep the top solutions and try to study how the secondary performance measure, that means the second objective, will behave. In this case, this approach is workable in the sense that, of course, you will consider two objectives, but the problem usually will be that you always optimizing one objective, and then another objective is actually negated in the optimization process. And that means you can have a chance that you get very good solution for one objective, but the secondary objective, in this case, like the cycle time, will be sacrificed because the optimization process simply didn't consider during the optimization run. And that's why we need to consider more advanced options. And then there are multiple terms here. Now I try to, maybe I will continue to talk about the first method here. We sometimes call it preference weight-based optimization. We not only combine the objective into single objective functions, we actually try to pioneer accumulations of the preferences assigned to the weight. And that means for the objective that you want to have more emphasis, you put it higher weight there. But the pioneer terms here is important because this is something that you should decide before you run the optimization, because the weight need to be decided before you run the optimizations. So that means it will be planar before the optimization process, as the English here has written. Now, we have another, I call it ideal, and compared with planar, we call it posterior. What does it mean by posterior? Posterior try to find a multiple trade-off optimal solutions with a range of value for all the objective. And that means you try to find the best trade-off instead of already put the trade-off into the weight, but you want to find the trade-off solutions and then you make the decisions afterward. And then the terms that we describe, we talk about Pareto, the same Italian economist who made this, invented this 80-20 rules. He called this a Pareto optimal solution because of the solutions that would be strictly superior to the other solutions considering all objective, but possibly inferior to other solutions considering one or a subset of objective. Okay, so the term that he defined is the optimal trade-off in English terms is defined by here. But it's not very useful if we just have the expression in English, because we need to formally put it into a mathematical formulation so that we can put it into an algorithm. And of course, we aim at finally, the decision maker can choose among those trade-off solutions. Let's take a look on the mathematical formulation. So the text I highlight here, so optimal solutions means that a set of solutions strictly superior to other solution considering all objective, but maybe inferior to other solutions considering one or a subset of objective. Okay, so it's very long English, but let's translate into English. We have two solutions. We try to compare them. How we compare them? We call it x1, solution x1 is set to dominate the other solution x2. So in mathematical terms, we can write that x1 is less than x2 in a special terms. I can show this term here. So this is sometimes we say that x1 and then it seems to be less than, but it's not the same. X1 less than x2 in order to say that is dominating other solutions. Now we have two conditions to fulfill. So the first condition is x1 is no worse than x2 in all objectives. So that means that none of the solutions you will find that the objective function value of x1 is actually lower than the other value, no matter what x2 is, when you compare x1 and x2, but it should be in all objective. But then how can we distinguish that x1 is better than x2 in terms of this domination? We call it, you find one of the objective, at least one of the objective among those m objective, that x1 is strictly better than x2. Okay, so if you look at this two comparison, this will fulfill the exact expression in English that we have seen in the last line. It means that we compared x1 and x2 by looking at all objective, and x1 is no worse than x2 in all objective, but then in at least one objective, it will be strictly better than. We can look at it also graphically. So graphically, if we compare two objectives, one of them is maximized. So f1 is maximized, and then f2 is minimized. Okay, then you could see that these solutions that I put up here, when I point here, in terms of f1, it has value that is higher in f1, and then in f2 is lower than this solution. Okay, and that's why we put them into two different levels, because we could easily see that if we call these solutions, let's just call these solutions A, and then this solution is B, then of course we could see that A solutions dominate B. Okay, but then now we have another solutions we try to compare. Let's call this A1, or we call it, let's just call it A1. I think maybe it's confusing. Let us rename it. I think it's better to call it C. Now, in terms of F1, okay, A is actually better than C, right? Because of A has a higher value in F1. But then A is actually worse than C in terms of F2. And that's why A dominate C in F1, but then C dominate A in F2. And this give we these terms called non-dominations. And that's what we mean by X1 is non-dominated by X2. You can have multiple terms to talk about it. So when we compare these two, so X1 does not dominate the solution X2, or X1, we can write it down in this multiple expression. We can say that X2 is non-dominated, X2 is dominated by X1 if X2 is dominated. But in this case, when we compare to A and C, we are not choosing the second term. So X1 is non-dominated by X2. So we call it non-domination. It's talking about they are on the same level. So by doing these computations, you can have a population of solutions. And then when you make this calculation using the formalism, I'll show it here, then you are doing the non-dominating test, non-dominating sorting, sometimes we call non-dominating sorting, which actually is a very important mechanism in multi-objective optimization algorithm in order to identify the solutions that are on the same level. So your goal is actually to get the solution on level 1, but sometimes you may have level 2 and level 3 and so on. But based on this calculation on the population of solutions, then you can get the different levels, and then in the same level, the solution are non-dominating to each other. So these are some classical examples. I think the middle one is from Professor Depp. Someone asked about the elimination. We will talk about elimination later when we talk about how the algorithm work. Okay, but a quick answer to you is if you are interested to collect all the solutions, then of course there is no need for you to eliminate those solutions. So let's say that if you have a pool of solution, you just do the calculation, then of course you have no need to say that, okay, you eliminate those solutions if they can stay there. Now, but the interesting question is, if you are working on an algorithm and you have a population, and that means your population have limited size. So if you evaluate 5,000 solutions, but then in your population, you just have 100, then of course, you will need to select the 100 solutions that are among the best in this level 1 and level 2. And then you go to the next generation. And that's why the elimination happened not in the domination calculation, but it happened in your algorithm when you move from one generation to another generation, when you use a genetic algorithm. So now we look at some practical example. You buy a car, and then normally you have more objective, especially if you need to consider buying a car with your partner, then you have so many other objectives to consider. But let's just say that you have two objectives. One is the cost and the comfort. And you need to understand how you look at this Pareto optimal front, or sometimes we just call it Pareto front. Now, all the solutions that lie on this front here, the red line, they represent the optimal trade-off. And we need to look at it by understanding the direction, because of if you start with an initial solution here, then you will see that the algorithm has two jobs to do. One is moving towards that direction. And this is a minimization, maximization problem. I like to draw this kind of arrow to show what I mean, okay? And then all the arrows will show you that the algorithm will work towards that directions. But not only about that, because if your algorithm just converge, that means you are doing a hill climbing, and then now you're going in certain direction, then it's not good because you want to cover a very good range. So in technical term, we call this diversity. So you're not only consider about convergency, you also want to be also diversified. And that's why when graphically, when we put this algorithm, we want to say that you want to start from somewhere, but you want to be covering, moving towards the direction. But anyway, if you look at the extreme solutions, 1 and 2, you represent the solution that satisfy you to the maximum range in one objective. So this car is the cheapest, but of course it gives you the lowest comfort value. But then the Rolls-Royce example here, this is the comfort value will be, even though it's subjective, but anyway, let's say that is the comfort level will be 90%, but the cost will be much higher. But anyway, you could see that no matter which solution you choose, A, B, C here, they are the optimal trade-off. What you try to get rid of or avoid will be dominated here or inferior solution. So for a car designer or a car manufacturer, of course, they want to strike that they can choose by their strategy where they want to put their product range there, where they want to market their product. But anyway, they don't want to be represented as something dominated. Now, look at this example. This example is something you can read about in chapter 8.2 in the Facts Handbook. This example talk about a hotel booking. Normally, the closer to some landmark, let's say that landmark building in Berlin or Paris, then usually you will have the cost much higher. So the distance and the cost, they are in conflict. In Germany, people like to put a cupcake here. I don't know how to draw very good a cupcake. This is a not very good drawing here. But anyway, I have seen people in Germany, they put a cupcake here to represent the ideal point. So in my next course, when we talk about this a concept called a reference point related to this ideal point, another point, I will come back and draw this to you when we talk about the reference point. But we don't talk about reference point in this course, but we just need to understand what we mean by choosing the solutions and then what we mean by dominated solutions. Why P is dominated by B? The reason was because of for the same objective, you see the cost. So B is no worse than P, okay? So B is no worse than P in any objective. But then B is strictly superior than P in terms of the distance. So if you have a certain amount of cost you want to pay for the hotel, why you need to pay extra if you get the same distance? If distance and the cost will be your single objective. And then when we look at this kind of a Pareto front, we also look at from another direction. Now let's see that C is no worse than Q in all objective, but then C is strictly better than Q in terms of the cost. That means with the same distance, you pay less for your hotel room. Even though this is a hotel room booking example, showing how you work with a minimization objective. But with these two examples, you could see that normally we were also looking at this line. When we later look at the practical production or supply chain problem, we will also look at the objective from this perspective. And then no matter what you do here, according to this posterior optimization process, of course, after you find the trade-off solutions, you will base on some higher level information in order to make the selections of the final solutions. So, but this process is done after you have generated the Pareto front, the posterior solutions. And then there are more examples here. So some of you have attended the lectures from Sunif Bandula. So he liked to use this figure to explain you have a maximization, minimization, and maximization problem. So I don't want to spend too long time on this slide, but I think this slide would be something interesting or maybe newer to you. This slide coming from picture from Professor Kring Fu Zhao, City University of Hong Kong. He used this figure to explain pretty interesting concept about where is the decision maker will be involved. So for a weight problem, the decision maker need to figure out the weight. And then in the strictly mathematical sense, normally people want the weight to be equal to 1. So that's why 0.3 here and 0.7 here. So combine that into 1, and then you can see that the objective 2 is more important because it has higher weight. But then the solution will be defined by the optimization. The computer here represents the optimization. You will automatically define A solutions. Now, compare with a posterior, the optimization will start first without asking the decision maker about the importance of the objectives. And then you generate the Pareto front. And afterward, this is why you call it as posterior, is that the decision maker will be involved in and then to find the final solutions. Now, there can be something called the interleaving or interactive. And this is a topic beyond the syllabus of this course, but it will be covered in next course. And that's why I talk about this reference point and also something more interactive. Interactive means that you first run some optimization, and then after the decision maker have seen some of the solution, he or she can now pick up a certain reagent using some graphical visualization or mathematical method. That's why we call interactive, in order to guide the optimization towards a area that is closer to the preference area of the decision maker. So in here, for the up here, when we go back to the first step here, you make the preference already before you run the optimization. And this one is now as posterior, is something you make after the optimization. But then you may waste quite a large number of computation in order to generate the whole Pareto front that to the end, you're just going to pick up a solution. You may say that interactive will be a trade-off of the trade-off in the sense that I have now seen another question here. I will come back to answer that question later when we have when we end today's lecture. But if I finish here, I want to tell that here will be more like a trade-off that you still want to get the preference from the decision maker later when she or he gets some information from the optimization, but then you don't waste a large number of computation in order to get the whole Pareto front, because of not the whole front will be useful. I think today I will, for my lecture, I will stop by showing you this animation in order to let you understand better what is the difference between a single objective. Now, for the single objective, I don't really follow this to 1, but I could put an R and C here. And for a production line problem, this production line is very simple. It looks like almost the same. If you are interested on how the line look like, okay. I will just cut. I think the line simply is look like this one, okay? So it's very simple line doing the buffer optimization. And then we have two objectives. One is the throughput, another one is the work in process. Now, in this, the left-hand side, I will show you an animation. And this animation comes from 4 optimization in different color. So for the first green color, it represents I put a lower weight on the throughput. And then gradually, when the color change, you will see that the weight become more important. Now, this is not normally people put the weight, because of people put the weight, as I mentioned, like Professor James' slide, he showed that you combine the objective into 1 so that you have 0.3 and 0.7 here. I simply make the effect of the throughput much larger so that to make sure that the solutions you get from different optimization will look very different. Now, I run the optimization now so that you could see, something wrong here. I think this is just a static picture. I think I make sure that it become a video last time, okay? After I save it, I think and then we open it, it becomes a static picture. Okay, then I think I promise on Thursday, the first thing you will see will be the animation. Okay. Now you bear with me. I don't think I have enough time to find back the whole video. I can find it back on Thursday. So I promise on Thursday, the first thing you will see will be the animation. I think when I save this PowerPoint into the Microsoft OneDrive, it has converted automatically into a static picture. I'm sorry about that, but if you bear with me now, you look at the figure on the right-hand side. You look at the figure on the right-hand side. This one is a bit more complicated, but again, the principle is the same. So whenever the color change, you could see that the value of the R and C, the weight attached to throughput and work in process will be changed. So in the beginning, the green color is something that we have a little bit more weight for the work in process, and then we reduce the work in process in blue, red, and black. But when the color change, you will see that the weight for the throughput keep increasing. Now, if the animation work, you will see that those color will be the final solution you find from the single optimization. And in this case, I'm comparing a pure multi-objective by the gray line that compare with the single objective solutions using the weight. You could see that the color more or less reflect the importance of the objective. So let's see that the black, because the black has very high weight in the throughput, 50 here, and much less weight for the work in process 0.1. And that's why you find solutions, the good solutions, almost always located in this reagent. But then in another example, you can find this from a textbook about production theory, about latex here. But if you don't want to look at this, you can look at the green solutions. Green solution have a bit higher, more weight in the work in process. You could see that it's located in the much lower range in the work in process. Now, the final thing you need to be careful when you look at this slide would be the gray solution is very nice, right? You see that the spread and the convergence is pretty good. Why we know that the convergence is also good? Because of it almost get the same solution that you get from single objective. So none of the gray solution, they are actually inferior to, to the single objective solutions. But then remember, when you look at the number here, you pay a higher cost. So this is something that lead to the discussions about why we need to have interactive. So for the single objective, using 2000 simulation iterations, we could already get the solutions at the peak with respect to certain objective. But to get this very nice Pareto front, you could see that I run 5,000 iterations. So that's why here is something important to learn. Yes, it's good to run multi-objective. Yes, you have a very good coverage about the whole Pareto front so that you can understand better about how it looks like the solutions on the objective space. And then you can relay it back to the decisions variables. But there is a course there. And this course is called a computation. We will come back to talk more about that, and then I promise I will definitely show you a video. Next time, I think I need to make sure that the PowerPoint open, because when I save it, it converted. Now, I want to answer one question. How would P is better than point B if it is minimization of distance? So with okay. You can read this, but I think how no, P is not better. B is better. So you see, B is the solution that is dominated. Sorry. P, I'm also confused myself. P is the solution that is dominated. That means you will choose B, and then you may choose a C, but you will definitely reject P and Q. Okay, because a B is the same course as P, but B is closer. You prefer to have a shorter distance. So P is better than P. Okay. This example, you can read it from the handbook 8.2, if I remember correctly. I have no time to give you a demo, but I think when we come back on Thursday, I don't know where even if you have started your chapter 7 and 8, but I will give you a demonstration on Thursday about how you set up a buffer optimization problem. And this time we will run the optimization together and then look at how Facts Analyzer can give you the non-dominating sorting. So the thing we talk about in theory, uh, how we choose the genetic operators, and then how we make the non-dominating sorting when we talk about in the later part. All this thing we will start with a demonstrations after the video. If you don't have any questions to me, then I think I will stop the recording.